Today we're going to learn the basics of chemical reactions. I'm going to tell you basically what's happening when chemical change takes place, and then I'm going to show you three ways that we represent chemical reactions or model chemical reactions so we can look for patterns and communicate about them. And then in subsequent videos we're going to learn how to predict what sorts of chemical changes are going to take place when we're faced with two different substances being put together. First of all, what a chemical reaction is a change in matter that results in the formation of different substances. So you start out with one thing and you end up with something that's completely different. So for example, boiling water would not be a chemical reaction because when you start out you have water and it's a liquid, and when you end up you have steam, which is just water in a different phase. So water becomes water. Technically a scientist would say liquid water L, water vapor G for gas. That's not a chemical change. Here's something that would be a chemical change. If I started out with water, like you did in a lab earlier in this year, and I split it up into hydrogen and oxygen, that is a chemical change because what I end up with is different from what I started with. In chemical change, what we start out with before the chemical change takes place is called reactants. Products are what you end up with after the chemical change has taken place. So in the example where hydrogen is reacting with nitrogen and producing something called ammonia, the reactants are hydrogen and nitrogen. Ammonia is the product. A chemical equation is an accurate written model of a chemical reaction. And what you've seen me drawing on the screen here are something very much like chemical equations. It's one way of modeling that a chemical reaction has taken place. Here's what their value is. First of all, they help us see patterns in reactions. When you write down equations for a number of different reactions that involve similar substances, you start to see that there are some patterns of change that take place in nature. Once you know the patterns, then you also are able to start making predictions about reactions. If these two things go together, what is most likely to happen? And can I predict what the products are going to be, even if I haven't done the reaction yet? So we're going to look at three different ways of modeling chemical reactions. The first one is verbal descriptions, where you just talk about it. You use words that will include the names of the substances, information about what their state is, possibly, like solid, liquid, or gas, and then a description of the change, like it burns or it decomposes or something like that. Here's an example. A lab burner flame, when you light the burners in the lab, here's what's happening. This is a verbal description of the chemical change that takes place at the burner. Methane gas, that's what comes out of the gas taps, burns with oxygen gas, which is in the room, to produce carbon dioxide gas and water vapor. So using words to describe that gives you a picture of what the chemical reaction is that's taking place. It's not just fire. To a chemist, there's something more fundamental going on with changes in matter. Another way of describing chemical change is using formulas. A formula description has reactants written on the left and products written on the right. And you've seen me write a couple of formula descriptions already. An arrow represents the change from reactants to products. A plus sign separates substances that happen to be on the same side of the change. So for example, our word description, our verbal description that we just had for Bunsen burner reactions, is methane gas burns with oxygen gas to produce carbon dioxide gas and water vapor. Well, if I were going to write this out as a formula description, I would have to know, first of all, what methane is. Methane is CH4. So I'd write CH4 burns with, well, that means there's another reactant, so I'll put a plus sign to separate them, oxygen gas. Oxygen is a diatomic, so O2. To produce, so there's words that indicate change, so I'll put my arrow in there to symbolize that. Carbon dioxide gas, prefix di means two, so carbon dioxide, CO2, and water vapor. So H2O is water. So that's a formula description for this reaction. Here are some additional symbols that can be used in formula descriptions to provide more information. One of them is if the reaction happens to be a reversible reaction, one that can go both directions, you can make a double-headed arrow like this. That represents a reversible reaction. The combustion reaction, the burning of methane wouldn't be reversible, so we would just use a one-way arrow. Solid. If you want to represent that something is solid, you can make a subscripted little s in parentheses. That means solid. A liquid could be represented by a subscripted little l in parentheses, and gas is a subscripted little g in parentheses. And then here's another one that's really common in chemistry. Lots of times reactants are dissolved in water, and so we call that aqueous. That's the word for that, and the abbreviation is AQ. So these are some additional symbols that you can throw into chemical formula descriptions to give a better idea of what's happening with the change. So for example, to go back to our methane gas burning reaction, methane gas burns with oxygen gas to produce carbon dioxide gas and water vapor. We could tune this up a little bit by putting methane gas, G, oxygen gas, little g, carbon dioxide gas, little g, and water vapor. Vapor is just another word for gas, so we'll put a G after that. Let's work this other example out. This says solid zinc reacts with aqueous hydrogen chloride to produce aqueous zinc chloride and hydrogen gas. So just reading through the reaction and writing down formulae, I can create this formula description. Solid zinc. Well, zinc is an element. It's just Zn, and it's not a diatomic. It says it's solid, so I'll put a little parentheses S after it. Reacts with. Well, that means there's another reactant, so I'll put a plus sign to separate the two. Aqueous hydrogen chloride. Well, hydrogen chloride would just be HCl. There are no prefixes there. And aqueous, dissolved in water, that means little AQ goes there. To produce. Okay, there are words, action words there that indicate that there's a chemical change taking place. So I'll model that with an arrow. Aqueous zinc chloride. Well, zinc is going to be 2 plus. Chlorine is 1 minus, so ZnCl2 is the formula. And it's aqueous, so AQ goes after that. And hydrogen gas. Hydrogen is one of our 7 diatomics, so I'll put H2, not just H, and then put gas. You try this one. Stop the video and give it a try, and I'll bring back an answer for you in a few minutes. Okay, we're starting out with solid aluminum. Aluminum is just a metal, and it's not diatomic, so it's just Al. And then an S indicates that it's solid. Reacts with, there's a plus sign. Solid iron 3 oxide. Well, iron 3 means 3 plus. Oxygen is a 2 minus, so when we charge swap, it's Fe2O3, and it says that's solid. To produce, there's my words that indicate change, so I'll put an arrow in. Aluminum oxide, it says that's a solid too. Aluminum's 3 plus, oxygen's 2 minus, so it's Al2O3, solid. And, so there's an arrow indicating there's another product, liquid iron. Iron is Fe, not diatomic, and an L for liquid. Try this one. Here's your answer. Acetylene is C2H2. So I'll just write that down. It says it reacts with oxygen, so that means there's another reactant, so I'll put a plus sign and then O2 because oxygen's diatomic. To give, there's my action words, so I put an arrow in to model that. Carbon dioxide, CO2, and water, H2O. Try this one. Stop the video. This is a little bit harder, but I think you can do it. I'll give you an answer in a minute. Here's your answer. Lead 2 nitrate. We'd have to write a formula for that. Lead 2 means 2 plus. Nitrate, if you look it up on the polyatomic ion sheet, it's NO3 1 minus. So when I charge swap, here's the formula I get. Pb NO3 in parentheses 2. And potassium iodide. So there's a plus sign. Potassium iodide would be K1 plus, I1 minus, so that's just Ki. It says these are both aqueous, so AQ, AQ. React to form, action word there, so I put an arrow in. Solid lead 2 iodide, so lead 2 and iodide 1 minus, PbI2, solid. And aqueous potassium nitrate. Potassium is 1 plus, Nitrate is 1 minus, so it's just KNO3. And then the AQ indicates that it's aqueous. For something to be an equation, what's on the left has to be in some way equal to what's on the right. And some of the things that we've been writing here as formula descriptions aren't really equations. Like, let's look at the burning methane example. CH4 plus O2 gives CO2 plus H2O. We can easily see by just looking at this that the number of hydrogens that we have on both sides isn't really the same. I've got 4 hydrogens here and I've got 2 hydrogens here. So at least one thing in this formula representation doesn't balance. If we happen to have a formula description that shows balanced numbers of atoms on each side, that really represents what's happening in nature in a real chemical reaction, and that's called a balanced chemical equation. But they don't happen automatically. Let's take another look at this particular reaction using models.
Here we're going to do this reaction, reacting methane, CH4, with oxygen. This is a burning reaction. This is what you do when the Bunsen burners are operating in the lab. The products of reactions like this are water and carbon dioxide. So let's take a methane, which looks like this, the black central carbon atom surrounded by this tetrahedral arrangement of hydrogen atoms, the little gray specks, and here's an oxygen, O2. Let's rearrange to try and make carbon dioxide and water. I know a carbon dioxide is going to have 2 oxygens attached to it and a central carbon. Well, there's a CO2, but when I go to make my water, all I have is hydrogens. There's not enough oxygen to make this happen. Let's look for a solution. I know that I needed more oxygen to make the water that I was missing in the last try, so I'm going to add another oxygen molecule and see if this will work. There's my carbon dioxide, and now I have 2 oxygens left over. Well, with 4 hydrogens, that's just enough to make 2 water molecules. There are my products, carbon dioxide and water. So clearly, to balance this, to make it work like nature really would work, I need to start out with 2 oxygen molecules, and I'm going to end up with 2 water molecules. Those numbers, the 2's that I put there, well, those are called coefficients. And we can balance reactions without actually building models. You can manipulate these ideas of atoms in your head and balance the equations without having to actually build models.
Balanced chemical equations are like math equations in one way, but they're unlike math equations in another way. Here's how they're like math equations. They're equal in number of atoms or moles of every element on both sides. So whether you're counting by the atom or counting by the mole, you're going to have the same number of atoms of each element on both sides of the equation. However, they're different from math equations in that, like a math equation, it's like 5 equals 5 or 10 equals 10. But really, what you have on opposite sides of the equation in a chemical equation are different substances. So you can see that a change has definitely happened when you look at a chemical equation. And so for that reason, we don't use an equal sign like they do in math. We use an arrow. So on the left-hand side and the right-hand side, there are some things that are alike, same number of atoms of every element on this side as there are on this side, but we don't use an equal sign because definitely something happened there to create new substances out of the atoms that were there before. How do you write a chemical equation? Well, the first thing you have to do is you have to start out with a correct formula description. So what that means is, to get ionic formulae right, you have to use charge swap correctly. You have to know what the charges are on your ions and then swap the charges, turn them into subscripts to get the correct formulae. And if you have a molecular compound in your equation, you have to use the prefixes that are in the name to get the molecular formulae correct. Another important thing when you're writing these equations is don't forget the 7 diatomic elements. There are 7 elements that always travel in pairs, and you can spot them easily by going to the periodic table and going to element number 7, which is nitrogen, and then making the shape of a 7, like I've done here. That gives you 6 of them: nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. and the seventh one is over here, hydrogen. So if you can remember that little pattern, it makes it easier. So every time you see those in a word description, never put just N or O or F. It's N2 or O2 or F2, and so on. Once you have your formula equation correctly written, list the number of atoms of each element on the left and the right. As you get better and better at this, you don't have to physically write these out. You can sort of do it in your head. But you want to know how many atoms of each element are on the left and then on the right. The last thing you do to bring this into balance is to add coefficients to the front of chemical formulae and symbols. You can never change subscripts because that actually changes the substance. But you can add coefficients to increase or decrease the number of moles of each reactant or product that's present. So let's go to our example that we had for burning methane. We've already seen what the answer should be, but let's try this method of listing out the numbers of atoms. For carbon we have 1, for hydrogen we have 4, and for oxygen we have 2 on the left-hand side. On the right-hand side, for carbon we have 1, for hydrogen we have 2, and for oxygen we have 2 here, plus another one there, so that's a total of 3. We can see that the carbon is the only thing that's balanced here. So then we have to look at what can we do to change the number of hydrogens and oxygens. Well, I'm missing hydrogens on the right-hand side, so putting a coefficient of 2 out in front of H2O would give me more hydrogen. In fact, it would give me the 4 hydrogen that I need. But that also changes the number of oxygens, because this implied 1 here is multiplied by 2. That gives me 2 O's in H2O. And then I have the 2 from CO2, which now changes this to a 4. Well, I could get 4 oxygens on the left-hand side by just putting a coefficient of 2 in front of O2. And that balances my equation. Now I have the same number of atoms of everything on both sides. Let's look at this again. Say I wanted to balance my water by putting a 2 here. Now I know that I need 4 oxygens on the left-hand side. Here's what I couldn't do to get myself 4 oxygens. I would not be able to change this 2 to a 4 because oxygen isn't O4, it's O2. So you can never change subscripts. Don't ever do that. You only balance by adding coefficients. Okay, you try this one. Balance this equation between zinc and hydrochloric acid to give zinc chloride and H2. Stop the video, give this your best shot, and then I'll come back with an answer. Okay, to start out balancing this, I'm going to list what I have on the left and the right side. Zinc, I have 1. Hydrogen, 1. Chlorine, 1 on the left-hand side. On the right-hand side, I have 1 zinc, because the subscript on zinc is 1. I have 2 hydrogens, because the subscript on H is H2. It's diatomic. And then chlorine, I have a subscript of 2. So what isn't balanced is hydrogen and chlorine. Zinc is okay. On the left-hand side, both hydrogen and chlorine come from the same compound, so if I put a 2 in front of that compound, I will change the hydrogen to 2 and the chlorine to 2, which brings this into balance. Try this one. Looking at the left-hand side, for aluminum I have 1 mole, iron, subscript of 2, so that means 2 moles, and oxygen, subscript of 3. On the right-hand side, aluminum is 2, iron is 1, and oxygen is 3. My oxygen's okay, aluminum and iron aren't. They're pretty easy to balance. If I put a 2 in front of the Fe, I will change that to a 2. If I put a 2 in front of the aluminum in the equation, I will change aluminum to 2, and that will bring it into balance. Try this one. On the left-hand side, I have 2 carbons, I have 2 hydrogens, and I have 2 oxygens. On the right-hand side, I've got 1 carbon, I have 2 hydrogens, and I have 2 plus 1, which is 3 oxygens. Hydrogen is the only thing here that's balanced. What can I do? Well, I need 2 carbons on the right, so I'll put a 2 in front of CO2. Now that changes my carbon to 2, but it also changes my oxygen, because now I have 2 times 2 O's in carbon dioxide, plus the one from water changes my 3 to a 5. Now here's a kind of a problem, because I need 5 oxygens on the left-hand side, but oxygens come in pairs, and there's no coefficient I can put in front of O2 that's going to give me an odd number. Anything multiplied by 2 will come out even, so I can't get 5. So here's what I'm going to do. I'm going to start this process over again. Now that I know that, I'm going to scratch out this 2 and go back to a 1 and 3 here. And then I'm going to put a 2 in front of the C2H2 and just double everything. Now I'll rebalance. I have 4 C's now on the left, and I have 4 H's. If I put a 4 in front of CO2, I now have 4 carbons, which will balance my carbon. But that changes my oxygen to 4 times 2 plus 1, which would be 9. But my hydrogen isn't balanced, so to make 4 hydrogens, which is what I need, I'll put a 2 in front of H2O. That changes my hydrogen to a 4, and it also changes my oxygen count again. Now I have 4 times 2 plus 2, so 8 plus 2, and that's 10. Well, now I have an even number of oxygens by doing what I've just done. So I can get 10 by putting a coefficient of 5 in front of O2, because 5 times 2 is 10, and now I've balanced the equation. This type of reaction you're going to learn later on is called the combustion reaction, and a good policy is to balance carbon and hydrogen first and then go to oxygen later. And the reason for that is oxygen shows up in 3 species, so you know it's going to be the hardest thing to balance, so leave it for last. Okay, try writing a balanced chemical equation for this reaction. I'm going to show you a little trick here that can save you some time. When I see nitrate, a polyatomic ion, or any polyatomic ion, doesn't have to be nitrate, and I see that it doesn't change across the arrow, NO3 on this side and NO3 on this side, I can balance that all as one unit and not consider the nitrogen and oxygen separately. So here's what I'm going to do. Make my list. 1 lead, nitrates, NO3 minuses, I have 2, potassium, 1, iodine, 1. On the right-hand side, still have 1 lead, nitrate, I have 1, potassium, 1, iodine, 2. Nitrate needs to change, and iodine needs to change. Well, I'll balance the nitrate first. I need 2 nitrates on the right-hand side, and nitrate is in KNO3, so I'm going to put a 2 in front of KNO3, which changes my nitrate and makes it what it needs to be, 2. However, that also changes my potassium to a 2. How can I undo that problem? Well, if I look back at Ki on the left-hand side, I can just put a 2 in front of Ki, and that will change my potassium to 2. At the same time, it changes my iodine to 2, and that's what I needed in the first place. So now my reaction is balanced. You'll have lots of practice doing quite a few of these in the upcoming days, and you'll get fairly good at balancing equations if you aren't already from previous classes. Next, we're going to talk about 2 kinds of reactions that are very common, that occur really regularly. One is where 2 things combine to make complex substance, and another one is when the complex substance decomposes. They're called synthesis and decomposition reactions, and that'll be our next topic next time.